Good afternoon, good morning, good evening from everywhere you are attending. Welcome to the third webinar with Professor Guy-André Boa. On my behalf and Jörg Leonard, I leave you in good hands of Jörg. He will moderate today's webinar. Just wanted to say hi and invite you to have a good session. Thank you. Jörg?
Thank you, Tony. Wait a second. Now I have permission to start a video. Welcome, everybody, to the third session with Guy-André Boa. I'm happy that we have Guy back. He guided us through a series of webinars. The first in September was about the evolution of automation. The second in October about the role of people in interconnected systems. And today we will hear about problem solving and procedures, how people handling unexpected situations. I think we introduced Guy several times. He is very much experienced in the field of aviation, but also space, and he is the one who coined the method and all the theory behind human system integration, and it's very, very useful for us in ATC to talk about that as well. Some of the things Tony asked me to do is that you will have, as always, the question and answer section where you can place your questions and we will discuss them on the end of the session. The session will be recorded, but the recording will be not published or made available if there are any questions. So please come back to Tony and myself and we help you as good as we can. So far for the introduction, Guy, I would pass the floor to you, and I'm looking forward for a third very interesting presentation from your side.
Hello, everyone. I share my presentation. Let me. Can you see my screen?
Yes, looks good, Guy. That's very good.
Okay. So let's start then. So today, okay, sorry. Today I'm going to talk about problem solving and procedures and how people are handling unexpected situations. This follows, as Jörg said, two previous presentation on the evolution of automation, the role of people in the interconnected systems, and especially dealing with complexity. Next time in February, I'm going to talk about several cases, use cases, not necessarily in the aviation domain, you will see. But today, let's concentrate on this. So the outline today is the following. The lecture is about procedures, automation, and problem solving in life-critical systems. So the question is, what are human factors that matter in this perspective? I want to talk about competence and this combination of creativity, knowledge, and experience. Sometimes creativity and experience are two very antagonist concepts, and we will talk about that. So I like also to talk about dealing with uncertainty and unexpected events. How could human and artificial intelligence complement each other? Where, we are in an era now where artificial intelligence came back with machine learning, deep learning, and everything like this. But it's interesting to see how all this evolved and how the concept of agent is very similar to the concept of system. Agent in artificial intelligence, in other words, is very similar to the concept of systems in systems engineering. So I like to talk about the complexity of human-machine teaming, and especially the maturity issue. We're gonna work more in the perspective of human-machine cooperation or collaboration and teaming more than using a tool. Of course, we're going to have tools in the future, but machines will be there to give advice sometime. And how much could we trust these machines? How much could we collaborate with them? Then I'd like to construct a vision from short-term prediction to longer-term possible futures. So it's this, I would say, distinction between, you know, event-driven behavior versus goal-driven behavior. You know, event-driven is very short-term. We need to react to events, and goal-driven behavior is more related to reaching a goal and trying to anticipate some future and try to make a plan to reach what we want to reach. So I'd like to start a discussion on risk-taking, prevention, and design. You know, when you have prepared everything that you, you try to prevent a lot of things, but an event arrives, occurs, and then you have to act. If you do nothing, you take a risk. If you do something, you take a risk. So what should you do? What do we mean by risk-taking? Okay, so we'll discuss about all these kind of things. So first, I like to present this, procedure following and problem-solving perspective. You know, in life-critical systems like air traffic control or flying or controlling a nuclear power plant, you know, always have operations procedures. So operations procedures tend to automate people. The people have to use the procedure, and sometimes, you know, you're watched as a human operator to see if you really apply follow the procedures, and if not, you may be punished. Actually, this is the problem. So in fact, you know, we are talking about automating human functions with the use of procedures. And when you put the procedure into the machines, then you automate. And then you automate machines, of course. And then this is a matter of automation of system function or machine functions. So this is rigid because this is done in very well-known situations, you know, expected situations. Of course, we tend to refine these procedures, we tend to refine this automation in more generic situations, you know, and then that worked a lot during the last decades of the 20th century and the beginning of the 21st century. We saw a decrease in the number of fatal accidents with an exponential tending to zero. And as a matter of fact, in civil aviation, I think 2017 was zero, so it was on the asymptote. It increased a little bit afterwards for some reasons, but you know, we made a lot of progress by developing procedures and automation. But what do we do when we have an unexpected situation, and even worse, an unknown situation? Then you have to solve problems. And, you know, at the moment, you know, the people are really unique for doing this. And because here we talk about autonomy instead of automation. You know, the agents needs to have the competence to solve problems and to try to, find solutions by themselves, but by themselves meaning probably in a group of people, in a group of experts, you know, and then you need to coordinate these autonomous agents. And in fact, you have to you have to coordinate the agent functions, in fact, in this case. So for that, you need flexibility. So this is the, you know, I wanted to compare the world of rigid procedures and automation to the flexible autonomy, in fact. And all this, we can summarize this as a human and function allocation. So the slogan, and this is what I'm doing right now in my chair at, in Paris, and we call, my chair is called FlexTech, Technology for Flexibility. And I will come back on that. So in fact, the slogan I want to throw and put on the table is how can we go from rigid automation to flexible autonomy? It seems that autonomy today is very fashionable, but let's think about what we mean by autonomy. When we talk about autonomy today in the engineering world, we think about autonomous cars or drones or things like this, but what about people, the autonomy of people? A friend of mine is in charge of a basketball team, and the players are handicapped. They are on wheelchairs. And in fact, they are, these wheelchairs provide them with lots of autonomy to play, in fact. And so in fact, the machine could be a FlexTech, a technology for flexibility. And it's not necessarily AI that is behind. It could be, anything that is, I would say, smart. So we'll come back on that. So in fact, and here, the really key point is that we worked for a long time on single agent automation, but here we are talking about autonomy in a multi-agent perspective. So I talked about that before in my previous lectures. I talked about the top model, technology, organization, and people. And in fact, human-centered design combined with system engineering leads to human systems integration. We are working on this within INCOSI, the International Council on Systems Engineering, and I will come back on that. So in fact, people are related to competence. We need to develop competence to handle this human-machine teaming. Technology is related to automation, and organization related to regulations. This is not an exhaustive description, but I wanted to give an insight of where we are going. In fact, with the competence are there to follow procedure and solve problems, both of them. And automation is actually a matter of artificial intelligence and data science today. Not only that, there are more than that, but it's human-computer interaction, the visualization of complex stuff, these kind of things also is part of the technology. But also on the organizational side, regulations are dealing with coordination, collaboration, all these kind of things. So I want to provide a schema that we ended up within the Human System Integration Working Group of INCOSI, International Council on System Engineering. I'm leading this group since 2015, and for the last 3 years, we meet almost every 2 months now, and we had a workshop, an international workshop, 2 weeks ago in Torrance, in the vicinity of Los Angeles, and we ended up with this diagram. It may look simple here but it took 3 years to put that together. In fact, we tried to define what HSI is about, human system integration. That involves systems engineering. This is becoming more and more very important engineering field with socio-technical systems, systems of systems, agile development, design and system thinking, and model-based system engineering, MBSE. So another discipline that enters into play for human system integration is human factors and ergonomics, with task and activity analysis, human and organizational performance evaluation metrics, and more than that, but this is to give an insight, as I said before. And then the third field that enters into play in human systems integration is information technology that involves human-computer interaction, artificial intelligence, visualization techniques, and modeling and simulation. And in addition to these three basic fields, then we have to add the operational domain. So in fact, if you work on cockpit design or aircraft design, it's different from air traffic control design or nuclear power plant design or medical system design. So in fact, the operational domain matters very much. So in fact, this is where you find the operational expertise and experience. This is where you can elicit scenarios, because we will see that scenario-based design is really key in HSI. And also experimental test personnel, test pilot, for instance, in aviation. So there is an inner loop also that we call the perspective space here, where you have safety that is important to better understand, competence and professionalism, sustainability, habitability, usability. Now we talk about UX, user experience, occupational health, social, cultural, and organizational factors, training, HSI planning, human factors engineering, workforce planning, and here, support and maintenance. So, we started with the basic fields, and then we go to the center by considering the three kinds of things I talked about already: technology, organization, and people within an environment. So in fact, this is the schema that we adopted within the INCOSY HSI working group to develop what we call today a primer. It's going to be a book of about 100 pages describing these various things, and so in fact, this primer handbook, for human systems integration will be divided in 4 volumes, and the volume 1 will be finished and delivered by the end of the year, so the next month. And then we're still working on the volume 2, 3, and 4, and we had this workshop 2 weeks ago in California to make progress on that. So you please, if you're interested in this field, keep in touch, and you could send me emails, and to see where we are. But also look at the website of INCOSY HSI working group, and you will see the progress that we're making. And of course, please, if you're interested, you could actually participate. So I talked about competence, and there is a competence evolution in aviation but in other fields as well, from flight quality control to management of embedded systems. My background is in cockpit design and evaluation and flight, so this is why I take some example on this, but this is pretty generic. I've been working with my PhD students on nuclear energy. I worked on oil and gas stuff, and I worked with automotive systems and also medical stuff. So, but let's talk about aviation there. Teaming up with machines increasingly equipped with artificial intelligence that we call human-machine teaming. What do we mean by that? And then we will actually try to better develop this in this presentation. Integration of software concept with physical concept. Sometimes we talk about cyber-physical systems. So the idea is to adapt to digital, keeping physical skills as well. I mean, we need to, I developed this concept of tangibility. If you're interested, I wrote a book in 2016 called Tangible Interactive Systems, where I tried to develop this concept of tangibility. This is when I was at NASA and also at FIT, the Florida Institute of Technology, where we have several examples of, and I will talk about that in February. I mean, I will take some examples on what we mean by tangibility. Tangibility is important in our virtual worlds that we are developing today. Sometimes people needs to better understand the physical stuff that is hidden behind the sometimes user interfaces. So tangibility could be physical, but it could be also figurative or cognitive. I already talked about that in my previous lectures. But physical tangibility is you may not see this, my screen, I mean my face at the moment, but I'm handling a pen, and I grab this pen. This is physical tangibility. I grab it, and I sense it. And figurative tangibility is more on the cognitive sense. I try to convince you, and if you are convinced, you say, well, this is tangible, what you're saying. That means that you can grasp the concept I'm talking about. You can grasp the abstractions I'm trying to develop. And then today, with these very digital systems, cyber physical systems that we are developing, we need to articulate physical tangibility with figurative tangibility. That's another point. And this is part of the evolution. And then we move from, the idea is this move from rigid automation to flexible autonomy. I already explained that in the previous slides. Another point is complexity management. Of course, I mean, when we talk about complexity, we immediately think about the opposite of complexity, that is simplicity. And then we need to simplify. I mean, what I learned when I was a student, in engineering, I learned to simplify things in order to solve the problems. The problem today is that the system is so interconnected that there is a property of these interconnected, very complex systems that is called separability. The biologists and physiologists understand this concept of separability for a long time. They know that, for instance, some organs in the human body are separable. Like, for instance, the hand, your hand, you can, replace a hand by, or work on the hand and then put it back. You have to be very good for that, but it's feasible. That doesn't work for the brain. You cannot separate the brain. I mean, you cannot work on it separately. So the thing is, now it's not like in the past where you could work on the system and dismantling it like a Meccano or Lego and then put it back. So you have to think about what is separable and what is not separable. So that's the first thing for simplicity, simplifying things. But the opposite of, the thing is, the opposite of complexity is not necessarily simplicity. It's sometimes familiarity. In fact, when you become familiar with a complex system, you find it simple. So, if you move from a region to another region and you live in a different region, in the first few weeks or months, you find everything very complex. And after a while, you get familiar with this complexity. Complexity meaning nodes and links. The bakery is there, and the drugstore is there, and another part of the city is there. And then in the beginning, it's very difficult to get familiar with it because you don't realize the interconnections between the shops, for instance, or things. And after a while, you know that the bakery is close to the butchery, and then you start to find this very simple. But in fact, it's a familiarization issue. So in fact, this is very important. And this is important not to think that by simplifying, cutting things into pieces and put it back is the best approach. Sometimes it is, but not always. It's better to understand the why, and sometimes you need the history of the city, for instance, to understand why this shop is there and not there. So for this, we use categorization approaches. We need to make categories of things, and this is a way to solve problem and categorization. A fourth point is collaborate problem solving. I will come back on that because I will talk about the Apollo 13 successful accident at NASA. And in fact, you can solve problem when you put several experts together and solve the problem, because somebody will actually find a solution that you cannot find yourself. So, and then you need to coordinate all this. So the idea is to develop a complexity culture based on experience, knowledge, and skill management. To develop and maintain experience feedback, this is important to capitalize, on the experience and actually integrate this incrementally. We've made a lot of progress during the last, I would say, half a century in cognitive science, where we understand how to integrate the experience in knowledge. Use digital twins technology. This term of digital twin now has become very familiar, popular in engineering. It's actually modeling and simulation of technology that we can use to better understand how it works. I mean, and when it doesn't work, then you can modify it by experience, and incrementally get to a better representation of that technology or that system. This is also probably what we could denote vivid documentation, if you like. So in fact, instead of writing kilometers of reports that sometimes very few people read, then you could have a digital twin that explain to you what is going on. So complexity is this. This is an example. I took that from the FAA when I was in the United States. They call that the NAS, National Aviation System. I had a PhD student working on this kind of thing, and this is the simplified NAS. So imagine the real one. She was working on the maintenance of airports, and then the system is extremely complex, and locally the people have different kinds of complexity because the suppliers are different and things like this. So in fact, so this is why categorization of tools and systems is a very important problem. So I come back on this separability issue. Let's imagine that you have a complex system, with the circles here represent people, for instance, and the square machines. And then you can separate some parts of the system like this, okay? The parts are represented by nodes that are related with links. In fact, this is and then the system itself is more interconnected, if you like, and but the complexity is not only in the nodes, but it's mostly in the links. If you look at if you take as an example the brain, human brain, we have thousands of billion of nodes that are called neurons. And then you have millions of billions of interconnections. And this is extremely complex. And when you put this at work, then you have the emergence of these yellow functions here that we call emergent or emerging functions. This emergence of functions occurs when you put the complex system at work. And the more you detect these functions, these emergent functions or emergent properties or behavior, the more you're getting to a mature understanding of what is going on. So maturity is really a matter of discovering these emergent functions. And then this is why I put the title, A Complex System as a Living Organism. It's not static. So in the title, I put life critical systems. I worked on several types of life critical systems for more than 40 years now. I got my PhD in 1980, so you see so if I put everything together with my PhD, it's 45 years. So I worked on space, especially at NASA, and in fact, what comes back all the time is a set of principles and property and criteria on safety, efficiency, and comfort. That comes back all the time, in life critical systems. But there are other systems, like, for instance, medicine, that is extremely complex. And the complexity here is on people. And then nuclear power plant, the life criticality is not only on the people who work there, but also the people and the surrounding of these machines. So one of my colleagues, René Amalberti, made this graph that was circa 2000, 2001, I think we were together. So he put the risk, the fatal risk on the axis, from 10 to -2 to 10 to -6 or 7, and he tried to classify, to make categories of life critical systems, going from mountaineering to cardiac surgery, professional fishing, medical risk, road safety, chemical industry, and then charter flights, anesthesiology, and blood. It's interesting because anesthesiology is pretty high here in safety. And then he classified in I would say, 3 main categories. Here there are 4, in fact, but there are, if you put together, in the beginning you have the classes of activities that are not regulated at all, and then the expertise of people is really the crucial thing. And then you have you start to have proceduralized systems, and then in the end you have what they call the ultra safe systems, where you have a really safety culture in the organization. So life critical systems, like aerospace, nuclear energy, medicine, you have safety culture, as I said, and this is where we are actually in aviation. This is very different in space, in fact, because in space we spend a lot of time, a lot of efforts in trying to master the complexity of system. But if you look at the experience of the space shuttle, American space shuttle, we had 135 flights and we had 2 fatal accidents. So that means that we are around 10 to the -2, and as in aviation and commercial aviation, we are around 10 to the -7. So in fact, this is really interesting to consider where you are there. So, and what are the acceptable domain of risk? And in systems engineering, you have regulations, operational procedures, and training programs. And this is this has been developed for quite a while now. And system reliability, human reliability, we have worked on this for many decades now. But the problem is, despite this heavy framing work, we still have to face unexpected situations that people have to manage in order to minimize consequences. Think about COVID, for instance. this was an unexpected situation, you know, and you can see that there were lots of disagreements even between experts. So this is the kind of thing I would like to talk about today. So let me tell you a story. In fact, that happened to me one morning. I was going to NASA from my house in Florida. I was in Cape Canaveral, and then usually I was you know, I had this stupid habit to wear my coat, you know, because in Florida it's pretty warm, pretty hot, but you need to take your coat when you're in your office because the air conditioning is so cold that you have to have a jacket. And so I usually when I went, you know, I was you know, I went down to my garage and then I used to put my jacket on the back seat. But before that, I was taking my smartphone and put it on the roof of the car. And then after that, after I put my jacket on the back seat, and then I took back the smartphone and put it on the dashboard of my car, and then drive on the freeway, and then go to work. That morning, I forgot the smartphone on the roof of the car. So, and I totally, I didn't think about. I mean, there was a kind of automatic action, you know, and act. And the smartphone was not like this one. In fact, I had a case, a rubber case, so for a while, the smartphone stayed on the top of the roof. And when I accelerate on the freeway, I heard a noise and I saw my smartphone in the mirror, rear mirror, and I said, wow, okay. So I thought about a lot of things, but the primary thing I thought about, I say, well, there is a lot of data on this. The guy will find the phone. You know, it's kind of, you know, from a security issue. I need to go back and find the phone. Well, I passed the story because there is more to say. But here, you know, can you imagine that a smartphone is a life-critical system? Because I couldn't call anybody to deactivate the phone. I didn't find it, by the way. And I was kind of very, very stressed because, you know, I just, you know, unexpected event, and I had to solve the problem. So for next time, I will tell you the follow-up on this. But what I wanted to mention on this slide is that sometimes you have life-critical systems that you ignore, and you're using them. So in fact, you have, you know, this is interesting because let's represent an expected situation. You know, I represent that by a line, but it could be anything, curved or whatever. And then, you know, the actual situation is something oscillating around this expected situation. You know, it's like an average of what you do, what you expect, you know, and things. And then the tolerance of this expected situation is called the, you know, probably noise, you know, a noise around this signal here. But in fact, it's a variability. And then suddenly happens a disruption, you know, something that you didn't anticipate. And then you have to recover. This is what we call resilience after that. So in fact, what I want to discuss here is this, you know, we try to associate filtering to variability management. And in fact, but the problem is it works, you know, linearly for a while, but at some point it doesn't work anymore. And then you are in a totally different cognitive space. So let's talk about stability, and we will come back on that. You know, when you have a stable system, you know, like something like that, this is a pendulum. The pendulum, when you have this variability, the red stuff here, you take the pendulum far away from the stable equilibrium, then the pendulum comes back passively to its passive situation. But you have another possibility. This is the inverted, in fact, where you need to be active to keep the stability, to keep the stability of the system. These people here are extremely dexterous. They are extremely skilled, to actually have an active stability versus the other one, passive stability. For any system, you have sometimes this passive stability, but for other, you need to keep the stability by providing reasonable actions. So here we are at the skill-based level, but sometimes at the knowledge-based level, it's more difficult. So in fact, this is the idea that I want to develop here. And in fact, in practice, for a long time during the 20th century, we simplified without taking into account the separability issue in complex systems. And then we adopted a linear approach, and then we cut the world into pieces, and we analyze each piecewise, and then we re-glued the things together. And we eliminated, the small parts, the p-values on the sides of this gauge curve, for instance. And this is where more and more the unexpected events happen. And then here we are not equipped with solutions to solve problems. This is a matter of context. How do we represent context? We'll come back on that. So let's take an example. In a safety analysis, most of the time, we have this formula that is being used. Risk is equal to the probability of the risk, the probability of an event to occur, multiplied by the severity of the consequence, that if this event happens. So the problem is when the probability is very small, let's imagine Fukushima, for instance. Fukushima, the probability was extremely small, even close to zero. But the consequence was very high. And what I learned at school in mathematics is that when you multiply 0 by infinity, this is the limit, of course, I mean, very small and very big, then it's undetermined. So in fact, this formula works on the hat of the bell curve, the Gauss curve, but not on the small parts, of course. And we by simplifying a complex system, we eliminate, this possibility of undetermination. So Fukushima is an example. For instance, in Fukushima, we know now that there were 6 earthquakes and tsunamis of that magnitude during the last 3 millennia. Don't ask me how they find this, but it's documented. So it means that it's very close to 0, but it's and for that matter, if you take the probability, if you take this formula here, the probability multiplied by the consequences, of course, I mean, it doesn't work because it's indeterminate. But if you take the possibility instead of probability, then the possibility is 1. So in fact, what matters is the consequences. So in fact, you see that by using some mathematical formula that are not necessarily correct, then you may end up with very serious problems. I'm talking about very fundamental things here. So in fact, the nature is complex. And when you simplify by linearizing some very nonlinear things, by putting local instead of holistic, then you end up with something that is actually very difficult to manage in the end. So this is again, this diagram that I showed you in the beginning, we try to keep being in this rigid space here with procedure and automation. But in practice, when everything is not going well and the rigid world doesn't work anymore, then or the expected situations are not there anymore, then you need to be flexible, and you need to have other kinds of technology, organization, and competences. This is another example. For instance, the DHL A300 cargo, that happens in 2003. In Iraq, the aircraft was shot by terrorists, and then they lost power, and they lost. In fact, what they use is the oscillation, of the aircraft to be able to land. I mean, these people were extremely skilled. So in fact, they managed to solve the situation because they were extremely skilled in aerodynamics and flying. So another example here is more at the organizational level. This Qantas A380 flight 32, where they had an engine problem, and in fact, the procedure, I think they had to use a procedure that was lasting 50 minutes or something like that. So, but in addition to that, they had very good things. They had two teams on board, and then they managed to keep the passengers quiet also, and then they, here they had to solve the problem by themselves. This is interesting. Another one is this US Airways flight 1549 here, where they had this flock of birds absorbed by the engines and take off, and then the solution was not very obvious, but the competence of the captain was was a very expert in flying with no engine, and managed to make a decision that was not really straightforward to land on the Hudson River, and then here there is a combination of luck and also really competence and problem-solving competence. So I'm talking about this kind of thing. So let's imagine that you have, let's imagine an iceberg here, where the iceberg is, in fact, is more complex than what you see in the atmosphere here. There is more than what you see. In fact, here is the conventional reductionism, what you see, and then here you have more complexity science stuff that you have to understand, and then so this is exactly what I like to emphasize here. You need to understand deeper knowledge at some point, and you need extensive training over a long period of time. What kind of training do you need to keep this physical and cognitive tangibility? Creativity, where creativity is key. And of course, I mean, people can make mistakes, and this is very difficult to accept sometimes. But sometimes you have no choice. I mean, the people have to solve the problem anyway. So creativity and procedure following are contradictory but complementary concepts. In fact, this is important. The selection of astronauts is based on that. I mean, this combination of these two skills. And there is also this fallacious expectation of zero risk. There is no zero risk on this planet. So again, I come back always to this diagram where we need to go from rigid automation to flexible autonomy. That doesn't mean that we have to forget the procedure and the automation, probably 99, I don't know the percentage, but I'll say 98% of the case, or 99% of the cases, or even 99.99% of the cases, then you will be in this, but sometime you will have to solve the problem. So I organized in 2008 a conference. I was elected in 2006 at the Academy of Air and Space, and I did this, introduction event to organize, and I choose to organize it on risk-taking. What do you do when you have prepared everything as much as the best you could, but an event occurs, and then you have to act. And I invited, several experts around the table for 3 days. They were astronauts, test pilots, surgeon, mountaineers. I had this guy, who is skiing in the middle of rocks like this and 140 kilometers an hour, and I invited people who were taking risk or who took risk, and they all said, from the surgeon to the people in charge of nuclear power plants, that preparation is key. And you need to prepare. If you want to do the Everest Mountain, to climb the Everest Mountain, you have to do a number of peaks in the Alps, and then probably before in small mountains, and et cetera, et cetera. So in fact, and what kills most of the time is routine. If you get used to do things, sometimes you're not precautionous enough. And then you may actually end up with a very dramatic problem. So abduction is really the inference that is being used most of the time. Abduction is you imagine a future and you try to demonstrate that you're right. That's the idea. Understanding, experience, discipline, in the sense of you have to be disciplined. You have to know the safety margins. Sometimes you cannot do things, and you have to know that you cannot do it. Availability and action. So let me take this example. This is a picture from the movie Apollo 13. Where this was a transcription of a real event that happened during the Apollo program, where the astronauts were stuck in the capsule, because they need to remove the carbon dioxide, and then they couldn't do it on board. So in fact, the people on the ground managed to make a system made of the devices that were on board the capsule, and then they sent the procedure to make this system. They send this procedure to the astronauts, and the astronauts made the device, and then they came back safe. So in fact, this is an example of collaborative problem solving or organizational problem solving. This is, it's not only one guy that can solve a problem in this case. In these cases where you have unexpected event, but a team. But you need to anticipate that. And to be honest, I've worked with people of the Apollo program. I was too young to be there, but many years after, I worked with people who were there, and I learned about this organizational problem solving. I mean, one of the motto of the Apollo program was, anytime somebody make a mistakes, everybody is there to help and provide, potential solutions and collaborate with the guy who is in jeopardy. So all this is about human systems integration. So one thing I would like to emphasize here, having worked within the NASA system for more than 20 years, what I realized is NASA was a very good environment where design and operations work together, probably in the same organization. EDF for nuclear energy was the same. we design. I mean, the people design the machines and the operations and run the operations in the same organization. So in fact, there was a kind of, if you think about people who are making aircraft and cockpits, and people who are making new air traffic control or air traffic management now, systems, and then we can work together to make a single system, a complex system that is articulated among the various actors. I call that holistic HSI, human systems integration. So it's like having an orchestra. To make a good symphony, you need to have music theory. The music theory is a common language. The musicians, whether they are conductors or musicians, basic musicians, or they understand each other because they have a common language. The second is the scores and the composers, the people who are making the coordination at the task level. What should be done. And then to make sure that the percussionist starts when the first violinist starts, for instance, or just after. This is do we have these composers today in the industry? I'm not so sure. They are low level or local level composers, but global level it's more complex. And then we need to think more in these terms today. Conductors are the people who are, the conductors are the people who are giving the tempo. And you don't play, for instance, a symphony at the Scala of Milan as you play it in the capital of Toulouse, for instance, okay? Because probably the public, the audience is different. And so the musicians, people are used to play with others, to collaborate, to compensate eventually a flow in the interpretation or things like this, and the audience, the people who are there to listen. If you'd like to know more of this, I wrote a book in 2013 that's called Orchestrating Human-Centered Design, that is actually using this metaphor of the orchestra in systems engineering and human systems integration. So for instance, let's take an example. An example here is you have two screens here. One is a screen of a controller, and the other one is a screen on board an aircraft. Two very, the similar situation here, but two viewpoints, two scores, if you like. And I try to to extend this metaphor. It's difficult to use metaphors because sometimes they are misleading. But and then there is a concept that is extremely important, that is called intersubjectivity. How do the people understand each other with different views, and the coordination of that. So if you take, for instance, the TCAS, if you have in mind this accident of the Überlingen accident, for instance, where you have the resolution, the traffic alert first, and then the resolution advisory, and you have times, and sometimes, for the Überlingen accident, there was a mismatch between the air and the ground, where the controller sent an order that was the opposite of the TCAS order, for instance. So the idea is the following. You have a task to execute, for instance, collision avoidance here, a role, a context, and resources that in order to transform that into an activity, usually this is a question of vocabulary here. The task is what you need to do, what the expectation, the prescribed, and the activity is the effective, what you have done, you're doing. And then the cognitive function in between the task and activity of for instance, a pilot or a controller as a role, okay, and a limited context, because outside of this context, the role is going to be different. And the resources that you have to use to make this function concrete. So in fact, the idea is if you have this in the head of a human, a pilot, for instance, and you transfer that into the machine. So in fact, imagine the TCAS, for instance, okay, the collision avoidance. instead of having a cognitive function that is actually coordinated by the controller, you have a new system here on board. The question is not the implementation only of this new machine, but these emerging functions. You remember the yellow functions I showed before, these emerging functions that you need to consider. You need to, for instance, here a cognitive function, emergent cognitive function is the role of the TCAS is to be considered first and not the air traffic controller order. So in fact, we call that human-centered automation. How do you discover this emerging function? And sometimes it's misleading. So in fact, if I consider, let's imagine you have this controller here with a cognitive function that is actually this anti-collision, cognitive function that is transferred into the machine, into the aircraft with the TCAS, and then you have emerging cognitive functions everywhere there in the. So we have to better understand if this TCAS probably should be connected to the STCA, for instance. It's not done yet, but so that's the kind of thing that we need to consider, and we have methods now that could anticipate that. So in fact, all this could be implemented using artificial intelligence. And I will not develop too much. I know that I'm probably Tony. How much time do we have?
I would say 7 minutes max.
Okay. So I go fast on this. The problem is, what is the maturity of this artificial intelligence that we implement in order to support, this FlexTech that we have in order to support problem solving. And then something I want to say at this point is a question is how mature are these systems? So we have a scale that is called TRL, Technology Readiness Level today. This was developed over the years, for the last 30 years. That was developed in software engineering at let's see, in the Software Engineering Institute in the United States. I know the guy, Bill Curtis, who developed that, but I don't remember exactly the university. And so I think that was in Pittsburgh. And so this scale, was refined and really nurtured by NASA. This is the NASA scale, in fact, of TRL. And then, today we think about that and we say, well, we need to have two other scales that should be coordinated with the TRLs. Another one that is related to people that we call HRL, human readiness levels. Are the people ready to use this new technology? Can we have a scale to measure that? And the other one is the organization. Is the organization able to be set up to comfortably, to efficiently, and to safely accept, this new technology? So in fact, in addition to the technology readiness levels, we need to implement organizational readiness levels and human readiness levels. This is also what we discussed 2 weeks ago in California. So in fact, back to this technology organization people model, top model, then you have these factors, like technological factors, consistency, easy access, etc. All this is very well known. Organizational factors, maybe less well known: communication, supervision, mediation, cooperation, coordination, conflict and priority management, all these kind of things. And that could be exemplified by this schema here, where you have 3 kinds of organizational model: the supervision, the mediation, and the cooperation here. I have really no time to develop all this, but if you're interested, I wrote a book 2 years ago called Human System Integration, where this is fairly developed. and we are continuing to do. And this is related to authority sharing. This is related to the level of knowledge that you have and the autonomy that you anticipate, you have, in fact. And sometimes you need to go from the highest level to the lower level. And then the human factors, situation awareness, decision-making, risk-taking, workload management, performance, trust, and collaboration. So all these should be coordinated. This is a concurrent engineering of technology organization people. Of course, you don't design people, but you design jobs, you design activities. And then today, we are in a reactive world. You know, we are in the short-term world. And you have the opposite is proactive world, goal-driven. You know, we have, in this case, we have these diagrams, you know, you follow. I remember during the COVID, we had in France every day the curve of, we're gonna have more deaths. We've got more people having COVID, and then we have less, and then we have more. And this is extremely short term. And instead, we have this goal-driven here. This is John Fitzgerald Kennedy, who said, I believe this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth. So did you know that? I'm quite sure that no, but there was an objective, there was a goal. And then the people worked, you know, like mad to make it real and created some motivation. I was one of them, motivated. I was a teenager at that time. So in fact, here we go from means to purpose, and here we go from purpose to means, which is different. This is about prediction. We want to predict everything, but short term, of course, the prediction is always short term. And then here we think about possible future, like anticipation, you know, science fiction, but in a good way. How can you anticipate things? Short term, longer term. Here is technology-centered engineering. Here is human-centered design. But what we will actually remember is this shift from means to purpose. I make a machine, and then I try to experience what you can do with this machine afterwards. And here today we say, what should be done? What I would like to do. Then after that, I develop the means to do that. You know, that's a better way. So we are developing, you know, after NASA developed this human system integration practitioner guide for many years, and this is the last version of it. Today, within INCOSY, we are developing this primer on human system integration. And the sources of my talk, if you are more interested in this, I use what we have done at the Air and Space Academy for quite a while now, and you know, air transport pilots facing the unexpected. There is a report on that. The HCIRO, some of you who are participating in this webinar maybe know these conferences. They ended up in 2016. They last almost 3 decades. Before 98, they was not named the same, but they actually started in 1986, I think. So in fact, it's almost, yeah, it's 30 years, and now it's they are blended into this conference, into the HSI conferences organized by INCOSY since 2019. So I wrote this document on risk-taking after a very interesting conference I mentioned in 2008 at the Air and Space Academy. This is a dossier of the Air and Space Academy. A paper in 2013 on dealing with the unexpected. And then the last book this year in 2022 with Edwige Kiyoru, we gather several contributions of a workshop that was organized in Florida, at FIT, Florida Institute of Technology, and this is the last production on these kind of things. And of course, aircraft accident investigation here. I've been an aircraft accident investigator for 2 years in the beginning of the 90s. So I know pretty much the field here, and thank you very much.
Thank you very much. Let's see if I can switch it on. Here it is. Guy, again, very interesting discussion, and you guide us very well through the topics. And what I always think is it doesn't look too complicated, but it's a lot of work to do to change our minds and follow a different way or a different approach. We have 3 questions, and Tony was so kind to let them with me, and I will try my very best to do it in the sense like Tony normally is doing that. The first one is about the unmanned aircraft systems, and the question is, what method would you recommend for the new industry to look at it and get started in a more systemic way with the remote pilot station and the aircraft automation?
You know, there are several, it's a very, very difficult question because that involves many things. It depends on what side of the question you want me to answer. So, of course, there is for me, the way I see it, and this is probably very personal, but this is my my experience. But I think the first thing to take into account is stability. You know, local stability. So in fact, if you have drones that are stable by themselves, you know, like these quadcopters, you know, that are basically stable, you know, you know, at the skill-based level. So in fact, you replace the skill-based. If I take the Rasmussen's model, you know, I introduced that during my first lecture. You know, you have skill-based behavior, rule-based behavior, knowledge-based behavior. The skill-based behavior is the level of the autopilot and things like this. So in fact, if you could ensure the stability at this level, that's pretty good, because it's like, you know, you can put the aircraft in a stable mode and solve the problem, like putting a satellite and on hold and solve the problem and come back on the to make the corrections or the maintenance. So that's one thing I would like to, you know. The second is actually the relationship with the other aircraft. In fact, you know, if you have drones in the sky, you know, if they are very well organized and proceduralized, you know, like in the air combat, for instance, you know, this is extremely proceduralized. But let's imagine you have a company that wants to deliver parcels. You will have systems everywhere. So how do you organize the sky? You know, how do you what are the road's rules? If I take the automobile metaphor, you know, you see on the road the difficulty we have in 2 dimensions, even in 1 dimension, because the roads are linear. But it's so imagine in 3 dimensions, 3D. So it's so that there is a very, very big issue here. How do we organize the sky? You know, that's and there are lots of colleagues who already are working on this. I mean, this is I know a good friend of mine from NASA is working at Uber, and they have a good team for that. But so that's the second point I would like to make. The third one is the recovery. I remember at some point there were some solutions, they would call that tubes. You know, when you have a failure, for instance, on a car, you can stop on the side of the road. In the sky, you cannot do that. So, what kind of resilience, recovery strategy and space do you have for that? That's another. And again, I mean, I didn't really work on this, but I discussed with a lot of people who are doing these kind of things. But this is this for me. There are the 3 points I would mention, but there are so many others.
Yeah, of course. But we can take, because the question was about a method, there is not a method in that sense you would suggest. It's more about raising different questions if you do your risk analysis or you design the system. So it's
Right.
bring in a broader spectrum what you had in the whole presentation today. Tony, do you want to say something? Because now you are my...
Just go ahead. Just pick up the next 2 questions, and I think the audience, we are starting to lose them. We still have 150 people in the audience.
Okay, I speed up. So the next one is a very interesting one. Is there any chance to have something from your method in a selection process? So when you hire people, how you can find the right ones or filter out the talented problem-solving people for your organization?
There are methods because the selection of astronauts is one. So yes, problem solving is. I'm not sure we can say that we understand everything, but we have a lot knowledge on this, and we have methods for detecting people who are pretty good at problem solving. So so that's one. Probably training on this should be better developed, and this is not a matter of you know, the last year of university, but probably very early school, because it's not only a question of you know, highly sophisticated technology development, but life for short, you know, and we will have problems to solve more and more in the future, I think, except if we accept that everything will be proceduralized and we'll follow the rules without saying anything, which I doubt that some people will comply to that. So that's the thing. So in fact, my answer to your question is, I think we should start as early as possible to talk about complex systems and non-linearities, because we teach the people on linear systems. You know, linear algebra is the, in mathematics, the most important matter that is taught, and we think that you know, non-linearities are too complex to be taught. But maybe we, you know, I developed a class of 45 hours at FIT when I was in the States, and it was pretty well received by people who are not necessarily mathematicians. So in fact, this is something that we need to develop, you know, these things. So and the method, you know, we are currently developing a method that's called PRODEC. I didn't talk about. Probably I will talk about more on an example on oil and gas later on in February. We are developing a method that actually is based on agile development and you know, the flexibility of design and development, and also the flexibility of systems that we develop. But there are tools. We are starting to have methods and tools. Yes.
I shorten a bit the next question. The next question is about what you said about a resilient behavior, or that people handling unexpected situations. The question is how to train teams or agents or people for something that we have no idea that it could happen, to be prepared for it.
I'm not sure. I have an answer, a straight answer to that, but we are working on it. This is the only thing I can say. You know, in my institute, we are trying to better understand. You know, when we talk about problem solving, the first thing that is important is not to solve the problem, but to state it. how do you state a problem? And you don't learn that at school. You know, what you learn at school is to solve a problem that is very well stated most of the time. And then you learn a mechanism, a grinder to get the solution, but it's based on problems that are already stated. So in fact, stating a problem is the first thing, the first method. This is based on creativity methods, idea generation, on you know, and we are developing methods for that for quite a while now, for the last 15 years. We have on creativity, and the problem is creativity when it's offline is different from creativity online. Online means you're in flight and you have to solve the problem now. You know, this is the question. So in fact, there are people who are better than others because they eliminate some issues better than others. But again, I mean, the risk is still there. There is no zero risk. So in fact, this is one of the things that we need to learn is to work in a non-zero risk environment, you know, and which we know for a long time in our field, but still, I mean, it's kind of taboo, you know. We don't want to take risk anymore, but there are risks everywhere. You know, this is so. How do you handle that? You know, and how do you state a problem in a very highly stressed situation? That's tricky. You know, this is a. For me, it's a combination of two things that are contradictory. One is creativity, and the other one is experience. People who are very experienced are very conservative. And people who are very creative usually are not conservative. You know, they are on the progress and stuff. So, and the combination of the two is really the key. How do you combine these two things? You know, and this is the kind of methods that we have to develop, I think. But again, I mean, what I'm saying is, for you know, I talked about unexpected situations, but most situations are expected. So in fact, we need to keep what we have. Of course, I mean, I don't want to destroy what we have done so far, which is pretty good. But if we stick with that, in this complex, more and more complex world, because it's interconnected more and more, you know, with software, with networks, with then we need to know that there will be unexpected situation, not unknown. In fact, this is, you know, we can demonstrate that the non-linearity could be known because there are things that are known. Not by everybody. That's the problem. It's some people may know, but they most of the time you have these unexpected things, and you are not prepared to react in the right way. So, you know, that's so in fact resilience should be taught. Yes, you know, some people are more resilient than others, and that depends on human factors. If you're very tired, if you're, you know, it depends. Very stressed. I mean. And sometimes stress is good also. I mean, it depends. You know, that's this is another discussion. Maybe I should give another talk on this. But this is difficult. This is yeah. Okay. So I stop there.
Yeah, I'm just getting in my head if a pandemic situation is expected or unexpected, or is it just something we just haven't on our radar, or just ignored, or it's happened in different parts of the world. Let me see how much time do we have, Tony? There are more questions popping up. I would do this one.
Do one because we can take the other question in the next session that we have in February with Guy.
So maybe we take about the tacit knowing from Michael Polonius. So the question is, if you somehow refer to the terms of tacit knowing, which is created, as I read it correctly, from Michael Polonius. Is this something you are connected to?
Could you repeat, because I didn't understand the question?
Tacit knowing. I know about tacit knowledge from Michael Polonius.
Okay, I know what tacit knowledge is about, but we need to be more explicit on this because there's, I don't know.
Maybe we can offer to Clemens that you write it in an email, and maybe we can discuss it via email so that you get a suitable answer for that. And we take the others.
More generally, if I could get the questions that are posed in this chat and the Q&A, I would be happy to answer afterwards. But please send them to me.
Yeah.
Okay.
I guess you can see them if you go on the question and answer.
Okay.
They are saved on the Zoom platform, and we'll ship them tomorrow to you, Guy, and we take it from there.
Okay, so Tony, I pass to you for the final words then.
Yeah, just to thank you, especially Guy and all the participants, and to the panel, especially for your moderation, Jörg. We have another session with Guy next year, so we'll tell him meanwhile, because probably we'll hear it from him on the emails, but Merry Christmas and all the best for the end of the year. But on the 14th of February, we come back with Guy with cases from not necessarily our industry, but from different industries on the human system integrations. And the next one, in fact, we have in between, we have two sessions with Sebastian Doiner. He is the retired safety manager from Frankfurt Tower, an air traffic controller, with few cases from other industries. But on the just culture principle, we can learn very, very much parallels between those. One will be on a train accident, bad habling, and the other one will be on a maritime accident on MV Rockness. So first with Sebastian on 15th of December at 1500, and with Guy again next year on 14th of February at 1500. Many thanks and stay well, and all the best to all of you. Thank you.